Here we are. Okay, so welcome to session number 5, right? And this session is related to sorting, and this is the second part of sorting. Last session, we were talking about, issues about the sorting problem, the lower bound of the problem, right? And some algorithms, right? That solve the problem, but each of those has a, its own complexity, we would say. And today we're going to continue with other algorithms. They work in a different way, right? As we did with selection, bubble sort, quick sort, in insertion sort also last week. So we're going to continue today. And just a reminder, it's about the first 4 homeworks. They should be submitted this coming Friday, right? And I'm going to open a tutoring and practical session on Friday morning, right? Just to give you some advice about, the final advice on your solutions, and also a practical session, similar exercises to what you will find in the midterm exam, right? So just prepare your submission before midnight on Friday. And then today I will give you the homework number 5, but homeworks number 5, 6, and 7, they will be submitted later. I will give you the date, but I think it's going to be just after the Easter week that we are going to have, right? So is there any questions, any inquiries that you may have now, up to now? It is possible to move the delivery for Saturday. Do you all agree? Is that okay if I extend the deadline? Or you are okay? Or, well, I have a particular request, but okay, so what I'm going to do is to extend the date until Sunday. Is that okay?
Yes,
Yeah,
doctor. Thanks.
yes,
Yeah.
yes.
All right, so okay, so I'll do that, and let me see, because someone already submitted homework number 1, and possibly the system doesn't allow me, to do the change, but let me try, right? So just consider now that the submission, the deadline, the submission date will be on Sunday, right? Instead of 14th, it's going to be the 16th, right? And that is okay, because next Monday we won't have a lecture here, but it's okay. Take it as a break, right? So work hard in the weekend until Sunday, and then you upload the homework and everything, and then you can take a little rest on Monday. Is that okay?
Okay, Professor. Thank
All
you.
right, good. Okay, so I will send you the announcement for the session on Friday morning, right? And the intention is just to give you about 5 exercises. So we do a review first, and then I give you 5 exercises, and then you try to solve them. I give you some hints in how to solve them. And then Friday in the afternoon, in the evening, I post the solutions in Canvas, right? Just for you to I can give you the solutions, and you can just check it out. But yeah, thank you, Cesar, for your reply about that you submitted. But let me check in if there's no problem, or if there's a problem, I let you know. So we try to solve the problem together. All right. Okay. So in this session is regarding sorting, but is the second part, as I was saying. And so we are going to check some algorithms also in a demonstration for the merge sort for the general case. We do the analysis also for the sort. And at the end, we are going to show the demonstration for the lower bound of the sorting problem, but in the average case, right? Because the previous session, we talked about the lower bound of the sorting problem, but in the worst case. And now we are going to show that lower bound in the average case. At the end, both the lower bound in the worst case and the lower bound in the average case are the same. That is n log n. So but I'll give you the demonstration there. So in some points of the presentation, I'm going to go very slow because there's some details that I need you to understand. Remember, the demonstrations are not for memorizing, just, as a procedure to show what we want, but also the use of different tools, to present the results of the demonstration. So let me just start. So previous session, right, talked about lower bound of the problem in the worst case, and then some algorithms, right, and some somehow some conclusions, about the topics. And now we are going to basically check three things. One is the merge sort, the other is the heap sort, and at the end is the lower bound, the lower bound of the problem, but in the average case, right? So these are mainly the three things we're going to review today. And at the end, I will talk a little bit about the homework number 5, but up to now, you don't have to worry very much about homework 5, but you should know what you're going to do, right? That is important. Okay, so when we talk about merge sort, right? So we are talking specifically about this process, merge, and this we'll see. So we have an array, right? An unsorted array, usually, and we are going to do a process called the merge sort, and we expect, to have the sorting array, the sorted array at the end, right? Usually we say that the array is sorting in ascending order, but you can always sort in the other way around, right? Descending order, doesn't matter. And then we use this concept of merge, right? Does anyone know what the merge does? It's a procedure, right? For doing what?
To combine like two subgroups of our list.
Two lists or two arrays, and the idea is, right, that you have to put them together, right, in a single list. And what are the main features or the main feature of the two groups or arrays that you are going to merge? What is the characteristic?
They have a smaller size than the first array, and they are already sorted.
Yes, they could be same size. They could be any size, but the most important thing that you mentioned is that they should be sorted, right? In order to do the merge, what I'm going to do is to take two sorted arrays, and I'm going to get a single array, right? sorted, right? So that's the process that merge sort does. So merge in particular, right, is this. So you have the sorted lists, and one of them is same size, and the other one is n size. And what are you going to get? Well, you do the merge process, merge, right? And then you get an array, right, of size n plus n, and the array, the resulting array is going to be sorted. Is that okay? It's well understood, the process of merge, right? So what you basically do in the merge process is you take this element and you compare, right? And then you say the smaller element, you're going to put it, let us suppose that the element in M is less than the element in N, so this element is going to come here, right? And then continue this, and there's a comparison there. The smaller is going to be put here, right? And so on. Do you see there's a kind of zigzag comparing between the elements, right? And taking the decision what the smaller element is, and then you put it here. So you are constructing the list, right, in ascending order. Is that process okay? Well understood? Yes? No? Yes. Okay. So I assume that you're saying yes in your mind. Okay. So this is the first exercise. Tell me, right, the complexity of the merge in the worst case. So you know how all these concepts. Now you manage all these concepts already, you know. And then let us suppose that I give you a procedure here, the resulting of the procedure, and I ask you, what is the complexity of this algorithm here?
N log n.
Okay, so let me just put it here. You say n log n. N log n is related to what?
The lower bound of the sorting
Sorting, right?
algorithm.
Sorting. So I have n elements and I try to sort them. But there's a
Yeah.
special condition here in which you have this one is already sorted and this one is already sorted. Does that make a difference? A difference for the complexity of the merge?
No, because you still need to make n comparisons.
But n comparisons?
Oh,
In
you
fact,
meant the complexity of the merge only?
the merge only, the merge. This procedure, I have sorted, and I put it together in this way,
The merge would be
right?
The
And
minimum of
remember that
n.
it's doing comparison. So the question is how, what is the complexity of the merge, but in terms of comparisons,
Would be
right?
the minimum of m or n, maybe.
Well, closer. Someone says n. Who agrees with that or who disagrees with that? Tell me. I do a one comparison here, right? And two, and three, and four, and five, and six. How many? What is the number of comparisons that I need? Do you think that m is enough or n is enough? This is too much, right? N log n, because I don't have to sort all the elements
Yes.
again, right? And the mean of m and n is just a few, right? But not necessarily what we need. What do we need? What do we need? because this is the resulting, I'm going to have n plus n, the final list, the resulting list. So how many comparisons do I need? This is a kind of, question for the exam, right? So this is the reason I'm just pushing you and to say, okay, I understand the process,
But
and I need to compute how many comparisons in the worst case. Of course, in terms of what? M and N, right? Because they are not necessarily the same.
But still, the comparison would be m plus n in the merging.
M plus N, right?
Minus 1.
And here I just do 1, right? So it should be this one. So do you understand why n plus n minus 1 is the complexity of the merge in the worst case? All right?
No, could you repeat it, please?
I need to browse the complete list of elements here, right? And the complete list here, in order to say, where I put this element, etc. And for putting an element here, I need a comparison between two elements of the array, right? So I need to do this number of comparisons in order to guarantee that I'm going to get the merge, the sorted list, the final sorted list of size n plus n.
Why the minus 1?
The minus 1 is because remember the finding the maximum in an array. So you need to compare the first two elements, right? And with one comparison, you decide which one is larger or whatever. The same here, right? And then you continue doing the comparison, the comparison of the other elements. But here is that minus 1 comparison over here, right? It's like finding the maximum. I have a list of n elements, and the cost is n minus 1, right? In the worst case. It's the same here, more or less the same principle.
Okay, so it's subtracting that comparison with itself.
Well, because actually when you say, I will give you a shorter example here. So let us suppose you have 1, 2, 3, 4, 1, 2, 3, 4, 5, right? And you say the resulting array is going to be what?
Yeah, 10 array.
9, right? 4 and 5.
Yeah, sorry.
Okay, so it's the resulting array is a 9 element, right?
Yes.
Something like that. But you say I compare this, and I put the resulting here. So let us suppose that this place, this and this here. And the winner is this and this here. So if you count this way, right, the comparisons, you are going to get eight comparisons to get this, which is n plus n minus 1, right?
Okay.
Okay, so have that in mind, right? When we do merge, we are going to do n plus n minus 1, right? If if both arrays are equal, same size, what do you get?
2n minus 1.
2n minus 1. Yes. Okay, that's good. So have that in mind. Continue. Right? So let us now see how the merge sort works. Right? I have a list of n elements unsorted. Right? I divide up into two subgroups, right? Or sublists of size n over 2 each. Right? And then I do the same. I split it up, and then a smaller size, n over 2 squared, right? Same here. And what do you expect to get? At the end, you're going to have what?
The elements, the
Elements.
numbers in the list.
Elements, basically, right? And then you start going up, right? You assume this, and you are going to have sublist of 2 elements sorted, right? Sorted. And then and so on, right? When you have 2 sorted lists of 2 elements each, so you're going to use merge, and you are going to have a what? 4-element list sorted, right? And so on until you come up here and you have what? N over 2 elements sorted, N over 2 elements sorted, and then do the merge, and what you're going to have here at the end.
N over 2K to
N elements, right? Sorted, right? So I'm just showing you the process. What is the technique using this algorithm?
divide and conquer.
Divide and conquer, right? So I have the initial array, I divide up, and then start at the end, it's going to start merging, right? And coming from bottom to top, right? Sorting and getting larger subgroups sorted, right? Until reaches here is an n over 2 sublist sorted, and this one is an n over 2 sublist sorted, and then do the merge, then get what we want, right? The solution of the sorted array. Is that procedure understood? Okay. This is a regular divide and conquer. If it is divide and conquer, what you expect to get, right? In order to say what is in order to say the complexity of the merge sort, what would you do?
I would go to n equals 1. I know the depth is n over 2 to the k. So I can make that equal to 1.
All right. So you're trying to give me the conditions. Tell me the recurrence for the procedure. What is the recurrence? T
The
of n
first
is equal to what?
2 times,
2 subproblems, right?
Yeah.
What size?
n over 2 to the k.
No, at the first level, T of n,
Okay.
2 size,
Yes.
size n over 2, right?
Yes.
And then what should we add here?
Plus
And-
n minus 1. N and a half. No, n minus 1.
N minus 1. And what is that cost coming from?
The merge.
The merge of these 2 lists, right?
Yes.
If I have 2 lists of size n over 2, the cost is going to be n over 2 plus n over 2 minus 1. That is correct. Yes. Right? So that is the recurrence, but it's not the complexity yet. You have to solve it. If you go to the master theorem, what is the case? A is equal to 2, and C is equal to 2, and X is equal to 1. So this is equal. What is the complexity?
N log n.
N log n. Is that okay? So this is the process we follow, with all the things we do here It's a problem, an algorithm, and the complexity. And that it is, right? In particular, we know that this is divide and conquer, so we get the recurrence, right? And then we solve it in order to say, okay, the complexity of that algorithm is n log n. Is that optimal or not?
Yes.
It is, right? Okay, very good. Okay, so this is, and this is what Cesar is just writing here in the chat, right? The complexity of the merge and the recurrence relation for the merge sort, and then once we solve it, we're going to have this. Is that okay? Good enough?
Yes. I have a question there.
Yes.
If we know that the depth for divide and conquer is around complexity log n,
Mhm.
and we know that at each level
Mhm.
the amount of operations it's n, can we
Yes.
simplify by n log n?
Yes. Yeah.
Okay.
Yeah. Intuitively, you can say that, right? And that is correct. But if you want to be more formal about, you have to do all this process.
Okay.
Okay. And yeah, but you're right. Yeah, actually, what we are doing here is I have n elements, and then I have, since this is a binary tree, right? The depth of the tree is going to be log n. So I have log n levels, right? And each level I do a kind of work which is related to n, right? And then that is correct. The complexity is going to take n log n steps. That is correct. Yes. Good observation. Thank you.
Thanks.
Okay. So, and this is the process. This is just an example, right? So you go down first, and then once you have the elements, you have sublists of 2 elements each, and then you start merging, right? All the way up till you have the sorted array. So you go down and then you go up, right? Now, the algorithm looks like this, right? You're given an array and the start position and the end position, right? If a start is less than end, that is okay. So you divide up, right, into 2 lists. And then you go and sort the first side using a recursive call there, and then the half plus 1 to the end, the second part, and then you go to here. Once that you return here, you have both parts already sorted, and then you merge, right, the array from start to half to end, right? And then you, after the merge, you get the result, right? So this is the algorithm, right? And you already answered these questions. Which design technique does merge sort use? Divide and conquer, right? What is the recurrence equation? T of n is equal to 2t of n over 2 plus n minus 1. What is the complexity of the merge sort? We can say that n log n. And what is the complexity in the general case? Because here we may assume that n is equal to a power of k, right? But if we want to discover exactly, you know, what if n is equal to 18, for example, or to 45 or whatever for the general case. So this is the demonstration that I have in the following slide, right? This is the general case. And remember, you don't have to memorize this. Just, you know, understand the process that we're going to follow. So I need your attention here in order to this demonstration. So I have n is any value, right? And what I'm going to do is T of n, the recurrence. You know, if this is a power of this if n is a power of 2, right, I get 2t of n over 2 in this part. But if not, I'm going to have, right, what is Tn over 2? This is the function floor, and this is the function ceiling. Tell me what the floor function does, and tell me what the ceiling function does, please.
The floor function rounds down and the ceil function rounds up.
To the integers closer, right? This
Yes.
one, the closer to the integer down, and this is closer to the integer up, right? And this is n minus 1. No, the same number that we had in the previous recordings, right? So up to here, we are okay. So remember to interrupt me or whatever, in case you have any questions. Good? So up to here, that is okay, I suppose, right? So for example, if n is equal to 11, what is the value of this? T of what? T of what?
6.
5, right?
Uh,
And this is going to be n over 2. The ceiling is going to be 6, right? So that's the difference. In fact, it's just one value of difference between these two. But we are going to follow, all the steps, Okay, so the demonstration is going to get this value. And this is n ceiling of log base 2 of n minus 2 to the ceiling of log base 2 of n, right, which is basically n, right, around n. And this is a constant, so this is the most important term here. And the complexity is going to be n log n. So this is what we want to demonstrate here in these steps. Okay, so at the end, this general case is going to be n log n. That's the conclusion, right? But let's go to the steps here. Okay, so this is the equation number 1 here. And this is what we want to achieve. And if I have one element only and I want to merge, I don't do any comparisons, right? If I have 2 elements and I want to merge them, I need to do what? Just one comparison. Is that clear enough? So I'm stating here the initial conditions, right, for the recurrence. There is recurrence that I want to show. Is that okay? Yes? I cannot hear you, but
yes.
okay. So, all right. Okay, let's go to the next step, right? If this is the function for T of n, what if I use n plus 1? So it's going to be n plus 1 over 2 floor, right? N plus 1 over 2 ceiling. And then here I would have n plus 1 minus 1. So that's the reason I get n there, right? So I get the two cases, the T of n, I have it, and the T of n plus 1. Is that okay?
Yes.
Are you following me? Yes. So I have these two equations, right? One equation, two equations. Now, what I'm going to do is T n plus 1 minus T of n, and I want to see the difference between these two recurrences, right? So the first one is T of n plus 1 is this one, equation 2, right? You see this one, this one, this one is this one, minus this equation. So it's going to be minus Tn over 2 ceiling minus Tn over 2. No, this is floor, this is ceiling, and this is minus times minus. No, minus times plus is minus, and minus times minus is going to be plus, right? So I have this expression here, less this expression here, and let's see what we get, right? So you have floor here, ceiling here, floor here, ceiling here. So let us observe. Up to now, is that okay what I did up to here? Because I'm going to change the slides. Good. Okay, very good. Okay, we are doing okay. Right now, we need to consider both cases when n is even or n is odd. For all the possible cases that I have n over 2 floor, n over 2 ceiling, n plus 1 floor over 2, n plus 1 over 2 ceiling, right? And let's observe what I want to do with this table is to put, all the elements here in the same term. And the same term that we are going to use is n over 2 floor, right? Because I need to manipulate later the expression in simplify. Okay, so if n is even and I do n over 2 floor, what will I get? N over 2 floor. That is okay, right? Is that okay? If n is odd, right, and I apply n over 2 floor, what I'm going to get is n over 2 floor, right? For both cases, I get even or odd. I'm going to get n over 2 floor for this case, right? Now, if I apply n over 2 ceiling, when n is even, is the same as saying that n over 2 floor. Does that make sense? For example, if n is equal to 10, and I apply this n over 2 ceiling is 5, right? Which is the same as doing n over 2 floor. You following me?
Yes, professor.
All right. And then, but if n is even, n is odd, I'm sorry, and you apply n over 2 ceiling, what you're going to get? N over 2, first you round down the number and then you add 1, right? But here I have the term n over 2 floor. So if n is odd and you apply n over 2 ceiling, you are going to get n over 2 floor plus 1. Clear enough? Clear enough? And it's the same for all the other cases. So if you have n is even, right, and you apply n plus 1 over 2 floor, is the same as applying n over 2 floor, this part. Yes? And you can check the other cases, but at the end, what I'm having here is all the elements here in this table in terms of n over 2 floor, which is okay because I want to use this table in order to compute this, because here you have n plus 1 over 2 floor, n plus 1 over 2 ceiling, n over 2 floor, n over 2 ceiling. But all those cases, right, are in terms of n over 2 floor. Now, observe this. These two cases are the same, right? For n is even, these are the same. And for n is odd, these are the same. And in fact, in the equations here, n plus 1 over 2 ceiling. N over 2 ceiling. N over 2 ceiling is this one. And this is same to n plus 1 over 2 floor, right? Which is n plus 1 over 2 floor, right? This is the same as this. And they are, this is subtracted from this one, so I can eliminate this too, right? And I can just leave the other in the terms that are given here, which is n over 2 floor for the cases and n over 2 plus 1 for the two cases. So what I'm going to get is something like this, right? This is for what? N plus 1 over 2 ceiling, right? N plus 1 over 2 ceiling is this expression. It doesn't matter if it is even, if this is odd, I have n over 2 plus 1. And for the other case, n over 2, this floor, right, is going to be n over 2 floor. So I have this expression, Tn plus 1 minus T of n is equal to, this is the case for this, and this is the case for this. The other two were eliminated, right? Plus 1, why? Plus 1. I had n minus n plus 1. So the only element that I have left is 1. So I have this expression now. Okay, so up to now, is that clear? No. If
I
not,
got
tell me
confused on
where.
how you chose if either using n ceiling or n floor for to solve
Because, yeah, that, you know,
Yeah.
here is the key point here. Because
Okay.
in the equation, you observe the equation here. I'm going to erase a little bit.
I have a question on the table you made. The first row are the floor and the second row are the ceiling or
No, it's n is even, right?
yeah, it's even
And then you apply n over 2 floor. And what you get? N over 2 floor.
yes.
If
Yes.
n is even and you apply the ceiling function,
Oh, okay.
but you know that n is even, you get n over 2 floor. It's the same,
Mhm.
right? And so
Okay.
on. So
Now
I
that's
have
clear.
all the elements here in the table are n over 2 floor, right? And these two elements, the n plus 1 over 2 in the equation, n plus 1 over 2 in the equation floor, this one, or ceiling. Floor is this one, right?
Yes.
And the other element 10 T of n over 2 ceiling, they are the same. So that's the reason I'm discarding these two elements, right? This and this,
Okay.
right? And I'm left with this one and this one, but in terms of n over 2 floor each,
Okay.
right? Because for the cases, for the both cases, in this case, n over 2 floor, they are n over 2. And for n plus 1 over 2, for two cases, they are the same,
Okay.
right? So I'm having this equation, right? This is T of n plus 1 minus T of n is equal to that, exactly what I was saying, right? N over 2, for all cases, is this one, right? And for n plus 1 over 2 ceiling is this one, right? N plus 1 is because I had n minus n plus 1, right? Up to here, question 3. It is okay? Yeah. Thank you, Cesar. Thank you all. Okay. Okay, let us continue. Right. Now, we are going to change variables here, and we are going to say that g of n is equal to t of n plus 1 minus t of n, which is this. See? So we're going to say that this part is g of n. And I have kind of the same expression here, t of n over 2 plus 1 minus t of n over 2 floor, both of them, right? So how, with this change of variable, what is this? What is this part? That part is g of n over 2 floor, right? Because this is n over 2 floor, and this is n over 2 floor. So if this is g of n, this is going to be g of n over 2 floor. Do you follow me?
Yeah.
And then this plus 1 is here. So I have a simpler expression here, right? G of n is equal to g of n over 2 floor plus 1. Add 2 now to this equation 4. Are we okay or not? Breathe deeply and tell me if you understand up to equation 3 and 4. Do you agree that we are having this recurrence, right? Yes or not? Can we continue, or tell me if you have any questions, something that you didn't understand, please. Clear enough? Can we continue? Or is there something that is not clear yet? Up to here. Up to here. Because we are going to continue. We need to solve this equation, right?
Professor, sorry for the question. I think it's basic, but why are we subtracting the t of n plus 1 minus the
And
t of
this,
n?
the intention is to get a number that we can manipulate later with the what is going to happen is that this expression has similar elements to this one, and it's going to leave me with some terms that I can manipulate. At the end, I'm going to just return to the original equation, right?
Okay.
So, and you're right, we are still manipulating the difference here. But remember, what we want to get is a t of n, right? But we are using this subtraction because we know that the two equations, or the two recurrences, have a similar elements that I want to discard, and then I just keep the ones that I need, in order to get what we want. Right?
Okay. Thank you.
Okay. Something similar we did with the, the average case of the quick sort somehow. Right? We use also the a of n and a of n minus 1 or something like that. But it's the same idea. So I have this equation, and you see, do you think you can solve this equation? G of n is equal to g of n over 2 plus 1. Well, let's do it. Right? We need to solve for g of n first, and then g of n plus 1, as you see here, is equal to what? To g of n plus g of n, right? So we are going to have the result here. Now, let g of 0 is equal to 0, g of 1 is equal to 1. You observe this, right? This is the equation here, right? G of 0 is, well, 0 is 0, right? And 1 is G of 1. It's going to be 0, it's going to be 1 here. 1 over 2 is half floor is 0, and this is 1. So that's the reason you have these two values here. Now, let us assume that n is between this range. Imagine n is equal to 13, for example. So this is greater or equal than 2 to the what? 2 to the what? Here. 2 to the 3. Q is 3, and this is less than 2 to the 3 plus 1. Right? Remember that this is the general case. It's not a power of 2. Right? So I give a value to n, whatever, and n is going to be between these two powers, right? In this case, 2 to the 3 and 2 to the 4. 13 is between those two powers, and q is 3, and q plus 1 is 3 plus 1. Is that understood here? I'm just stating the value of n, okay?
Yeah, it's okay.
Okay, so and then we are going to do this. We are going to solve it by substitution, remember, right? So I have the original equation here, and then I say this equation is going to be this gn over 2, right? Which is this, plus 1 plus 1, plus 1 plus 1, which is 2, right? So I have n over 2 squared plus 2. So that's the first step. After getting q steps here, q steps. Why q? Why q steps? Why q steps? Where do I want to stop in the recursion, in the substitution? When? Because here I'm going to have n over 2 squared, n over 2 to the cube, n over 2 to the 4, etc., etc. So where do I want to stop here? N over 2 to the cube. What is that value you're going to get? N over
The
2
level
to
when
the
you have
cube.
the final element.
Yeah, What is that value?
1.
Is 1, right? G1, which is this G1 is where you're going to stop. And that's the reason you're going to do Q steps, and at the end, you're going to have Q plus 1, which is, if you get the log of n of this number of 13, what are you going to get? The log of Q plus 1 is going to be that which is log of n ceiling, right? You get a log of n ceiling of 13, and you're going to get 4, which is Q plus 1, which is this number here. Make sense? So I'm linking several things here. The value of n, which is general. N is between these two values, two powers, right? Q is this one, and Q plus 1 is this one. And when I solve a substitution after Q steps, I'm going to get Q plus 1, which is log of n ceiling. Are we doing okay? Yes or not? So the value here is G of n is equal to what? To log of n. This G of n is log of n ceiling. What do you think? Good or not so good, or not good at all? Tell me.
Professor, can you, on
Yes.
the last step, how did you go from the left side to the right side before log n? That's the only part that
Right.
I'm not.
Okay.
that
Okay.
clear.
So I'm going to repeat this. Okay.
Yes.
Remember that I have a recurrence, which is
Yes.
this, right? And then I'm going to do it by substitution. So I'm going to replace this in the next step, which is g of n over 2 or times a half
Yes.
here, right? Because I have n over 2, which is it, plus 1, right? When I substitute. And the one that I have here, so that's the reason I put a q, 2 here.
Yes.
So, and I get, actually, this is a simplified version of this equation, which is g of n over 2 squared floor plus 2, right?
Yes.
And this is the first step in the substitution. Good?
Yes.
Now, consider that, you continue replacing this and you do few
Okay. Now I
steps,
get it.
right?
Yeah, and it will
So
be
you're gonna
until
have, instead of 2 here, you're going to have 2 to the q, right? N over 2 to the q in this equation. You see it?
yes.
And then plus q, your plus 1, plus 1, plus 1, how many times? Q.
Q.
And n over 2 to the q, if you see here, n over 2 to the q is going to be 1 because you're using the floor.
Yes.
And then you have g of 1 is 1. So that's the reason is you have q
Oh,
plus
okay.
1, right?
Yes.
And then you say, okay, q plus 1, which is this value, is the log of n ceiling.
Okay.
For example, for the example, you have 13. The log of 13 ceiling is exactly q plus 1.
Okay.
Up to now, we are okay, right? So the result of g of n is log of n ceiling. But remember, we have to return because g of n is t of n plus 1 minus t of n, right? Remember? So tn plus 1 is equal to this, right? And then I can solve by substitution again, right? T of n
Professor,
is t of n minus 1 my plus log of n minus 1 plus log of n here. T of n minus 1 is t of n minus 2, log of n minus 2, log of n minus 1, log of n, and so on. Yes, I'm sorry. Yeah.
don't worry. Is that log base 10 or base 2?
Now base 2. Usually what we use here is log base 2. And it's base 2 because what? Because we had a kind of binary tree in these operations that we are using, right?
Okay.
Now, I'm going to leave you this. This is a substitution, right? And then I'm going to have t of n minus I, for the ith step, and I'm going to have this expression, which is the sum of logs, right? From 0 to I, right? So 0 is n. When j is equal to 1, this is n minus 1. See? This is the summation of all the logs to the right of this, right? And up to n minus 1 steps, because I want to get here t of 1, right? So I'm going to do from 0 to n minus 1. sum of all logs there, right? And then I have the ceiling here. So this is T of 1 is going to be 0. That's the reason I discard this element, and I just keep this expression. How does it look? You have n minus 0 right at the beginning. So you have n, the ceiling. The log of n, the ceiling. And then when you have 1 here, you have what? N minus 1, log of n minus 1, the ceiling, and so on. When I have n minus 1, I'm going to get what? 1, right? Up to n. Log of 1, ceiling, log of 1, log of 2, ceiling, log of 3, ceiling, etc., right? So if n is equal to 13, for example, n is equal to 13, n is 13. The log base 2 of 13, right? Ceiling, what is that value? 13.
4. No.
12? 12? 4, right? Yes or not?
Yes, 4.
Remember log base 2 of that number ceiling. So for 13 it's going to be 4, for 12 it's going to be 4, for 11 is going to be 4, for 10 is going to be 4, for 9 is going to be 4. What is it going to be for 8? For 8, around here.
3.
3, right? So I have in for 8, for 7, 3, right?
3.
For
Until
6,
4 when you get 2.
so you will get for 8, for 7, for 6, and for 5, you will get value of 4, of 3, I'm sorry. Right? So you're going to have 1, 2, 3, 4. For this case, since n is general, 13, 2, you have 13, 12, 11, 10, 9, 5 elements with this value, 4 elements for this value, 2 elements for this value, 1 element for this value. So this is an increase up to here is an increase in powers of 2, right? And then I have these numbers, certain numbers, right, with value q plus 1. So I need to count all this, right, because this is what I'm getting here in this expression. So I get log of n minus 1, this is expression, 1, 2, 3, this is expression, and up to here, up to here is 2 to the q, and then this one up to n. So up to here is like 8. This is 9, 10, 11, 12, and 13, these numbers. So I can rearrange because I have 0, I have 1 with 1 value, 2 with 2 values, 3 with 4 values, and so on. And what is this? Tell me this value, n minus 2 to the q. What is that? Tell me this expression. What is this? Q plus 1. Remember. N is 2 to the q, and less than what? 2
2
to
to
the
the q
q
plus 1.
plus 1. right? So who is gonna have value of q plus 1? All the values from here to n. How many? N minus 2 to the q. And the others I have 1 with 2 with 3, and it's increasing by powers there. Up to what? Q times 2 to the q minus 1 plus the remaining number. So I'm counting all of them together, right? I manipulate with this expression here. I solve for s up to here, right? And I get the expression, which is this. I'm just moving forward, but it's the same. The manipulation is the same, right? For the result, this and the summation this here. This is the part here. This is the result of S. I manipulate, and at the end, I get this expression here. That is the one that I was looking for. And the expression, okay, here, what it's telling me in the general case is that this expression is n log n, right? So for the case in which n is a power of 2, the algorithm is going to work like n log n. For the case in which n is any number, for the general case, the complexity of the merge sort is going to be n log n. So, right? So don't memorize all this stuff that I just did, but I used several tools like changing the variable, solving, returning, right? Using the summation here in order to generate a new sum here, which is this S, solving S with the regular equation that we have, right? Because we have this expression. This is I, the summation of I, X, I, in which X is equal to 2. So I need to use the expression to solve it, and which is this. And then I use that part, put it together with the other part, I solve it, and then I have n log n. Conclusion. What is the conclusion? That merge sort is n log n. What is the problem with the merge sort? What's the problem you see with the merge? The complexity is okay. I mean, it's n log n. It's optimal algorithm, right? But what is the problem that you may face with the merge sort? The recursion, right? Because recursion is, I go one level down, and I need to keep all the elements there.
Maybe the memory space.
It's the memory space, because every level I need to keep, right, information. So
But
if
also
I have,
it can, one benefit is that it can be done in parallel, right? Or with multiple cores? Or
well, yes, you divide up. Once that you divide up, you send to a CPU, whatever you're using, right? To get the sorting of that part and the sorting of the other part. Once you have them, you can just join them, right? Yeah, now with the infrastructure that you have or that is available today, you can do a lot of things, right? But if you're running this in a single computer with a single CPU, probably your memory for large N, your computer is going to suffer a little, right? So that's the meaning of one of the exercises in the homework is related to that precisely, and see what you find. All right? So far so good. A little bit complex, that part, but don't worry. So just go in detail at home and then you say, okay, I'm okay with this, right?
Yes.
All right, so let us take a break and we come back at 5:30 and we continue with the heap sort, okay?
Good. Thank you.
All right, so I'm gonna stop the recording and then we continue at 15:30. All right, thank you. Recording again. Okay, so next topic is the heap sort. Heap sort is going to use a structure that is called a heap. That's the reason it's the name of heap sort. Okay. And we have the unsorted array. And we are gonna do the heap sort, and we are going to get the sorted array in ascending order. And let's check what the heap does, and then we are going to do some example, you know, to show this process and then the complexity. So a heap, what is it? It's a binary tree. Everyone understands what a binary tree is, right? So I have the root, I have 2 children, right, for each node, right? And at the end, I have a number of leaves, right, in the tree. So a heap is something that a structure that the leaves are at level D or D minus 1, D, or I can say that, for example, when the heap is not complete, the leaves are filled from left to right. For example, here I have how many leaves? 1, 2, 3, 4, 5, 6, 7, 8, 9 leaves, right? So this is level D minus 1, and this is level D. And what is the relation between D and the number of elements that I have, or the number of leaves that I have on the tree? What do you think it is? So I have level. This is level 0. This is level 1. This is level 2, and so on. And this is D minus 1, and this is D, right? So if I have 9, or no, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 9 leaves. What is the depth of the tree? Remember the depth of the tree of the n factorial leaves in the sorting? What is the relationship here? Log base what?
Base
Two.
Base 2, and the number of leaves here. So this is going to be at log base 2 of 9 is 4, right? And all the others are going to be 3, 2, 1, etc. 0, 0 the root. When the heap is not complete, if it is complete, for example, you discard these two, you have complete, all the leaves are at the same level, right? The last level. If not, one leaves are going to be in the D minus 1 level and the others in the D level, right? The element of a given node is larger. The element of this node is larger than the offsprings nodes, right? And this node is larger than these two, and this is larger than these two, etc., etc. So these are the conditions, you know, to have a heap, right? binary tree lives at level D or D minus 1, filling out from left to right if the number of leaves is not a power of 2, and then the condition of the values on the nodes, right? Always a node has a larger value than the offsprings, right? Does that make sense? Right? Okay, so let us do the example. So at the beginning, you're going to generate a heap. So this is the array, and you need to put it in a binary tree and then construct the heap. Let us do that, right? So is this array sorted already? Is it?
No.
No. Okay, so we are going to construct the heap at the beginning. So this element is going to be at the root, right? These two elements at the next level, right? These four elements at the next level, right? And the rest in this case is increasing exponentially, 1, 2, 4, 8, etc. But in this case, I don't have a power of 2, so these three elements are going to be in this way, right? So I have a heap with the number of elements in the array, right? Okay, let us just observe this. 26, 5 and 77, 1, 61, 11, 59, and the other elements here. Is this a heap? It's a question for you. Do you think this
No.
is a heap? Why not?
Because 77 is in the second layer,
Mm-hmm.
and in the first layer, 26 is like the parent, and
Mm-hmm. The
27 should
condition
be
that
big.
a node should be larger than the two springs, right? The two offsprings. So it's not met yet. So what we are going to do is to construct the first heap, right? So we are going to start this way. We compare these two, right? And the larger node is going to keep there, right? On top of the higher level, right? So this condition is okay for this sub-tree, right? Which is a sub-tree with just an offspring, right? And then we do the next one, which is here. We compare these two, and we take the largest, and then we compare it with the value in this node, and then we rearrange, right? So it's like constructing a small heap, and then we're going to increase the size until we have, until we have, the largest one. So in here, so we compare these two, and then the largest with this one, and then we give a heap. So we have a heap now here and here, right? Here we don't have heaps those size. And now we continue to this larger heap. So we compare these two, and which is the largest? 61. So we are going to move 61 here, and 5 is going to move here, but before you place it here, you go down and compare it with the elements at the lower levels, and then you try to give or arrange this heap. So 5 against 61. 61 is going to go up here. 5 is going to be here, but before placing it, you are going to compare it against 19. So 19 is going to go up and 5 is going to be in the last level. So I'm going to have something like this. You see, this is a heap already. Good. And now the other one is the same. This compare against this one, and then against 77, but 77 is the largest, so it's going to keep there. Okay, so that's in the next step. And now we compare these two. We take the largest, we compare against 26. So 26 is going to move down, but before you do that, you compare against the other two elements, the largest of the two elements here, and then it's going to move 26 here and 59 here. So it's going to look like this. So here we are constructing a larger heap, which is the heap that we are having, right? So 77 here, 26 here, but before you put it there or leave it there, you just move 59 to the level here, right? So the question is this a heap? No. Is it a heap?
Yes.
It is, right? It is. This is larger than these two. This is larger than these two. This is larger than these two. This is larger than this one. This is larger than these two. And so the condition is met, right? And we have a heap. So we used certain number of steps, right, to construct the heap. Now that the heap is constructed, what's next? What do you have here? What do you have there in the root of the heap?
The maximum?
The maximum. So where should I put the maximum? Imagine this is a tree, right? But this is the array. So this is the first position of the array. And this is the last position of the array. Since this is the maximum, what should I do? Go and exchange, right? This and this. Put 77 here. And once that you have 5 here, you need to rearrange the heap in order to say, I'm going to leave a heap now with n minus 1 elements, right? And I'm going to compare against these two, right? And 61 is the one that is going to now be here. And 5 is going to be here. But before I do that, 48 is going to go up here. 5 is here. But before I do that, I compare against the elements in the next level. So 15 is going to be here and 5 is going to be here. Is that a heap? 61 root, 48 here, 59, 15, 19, 11, 26, 5, 1. And here I have 77, which is already in the right position, right? Is that okay? Clear or not?
Wouldn't it be easier to already be constructing the solution with the maximum values of the heap?
Oh, yes. This is the maximum value again. So there's a cycle now. 61 is here. And then you're going to put in the 1 and put it in the right position. Right? And so on. So there's a cycle. After you construct the heap at the beginning, and then you do this cycle, because here you set 77 in the right position, and I have an n minus 1 heap. 61 is here, and I have an n minus 2 heap, and so on. Until what? Until I have all the elements in the proper position for each, right? So the algorithm is gonna look like this, right? Construct the heap. That's the first step in the algorithm. And then you do the cycle. Copy the key of the root of the array, remove the leaf at the last level and save this value. Rearrange the case when inserting the previous element in the heap in such a way that the property is established. So do you think that this algorithm shows what the heap sort is doing? Do you understand the two phases? One is to construct and the other is to construct the ordering, basically, right? Through a cycle here. You want me to go through it again with example? Or do you clearly understand what the heap sort is doing? Because next step is just to analyze what it's doing, right? In terms of the work, the operation that is doing. So, should I go again with the algorithm, with the example? Or do you understand what it's doing through these steps here? Do you agree that I need a separate part in the algorithm just to construct the heap? Because at the beginning, the array is not sorted, right? So I need to put it in the binary tree and then construct the heap. And once that I construct means that, the structure meets the conditions, and then I can start doing the cycle here. Okay?
Yes.
Okay, so let me see. And this is right. So actually, I have the example here. So I put the 77 here and the 5 I changed, right? But I moved 61 to up and then 5, 40, and then 48, 5 here. And then, right, I have now this is in the right position. And then I have this is the greater, right, of this heap, and then I do the same, right? I exchange 66 here and 1 I put it to the side because 59 is going to be here, and before I paste the 1 here, so 26 is going to be here and 1 here. So that's the second step, right? And then you arrange the 59 in the third position here, and so on, right? So just remember that for constructing the heap is the following, right? Let us suppose we have 8, 1, 2, 3, 5, 6, 7, 8, right? So what I'm going to do is try to show you the procedure, because we need to find the complexity for this and for this, and then the total complexity of the algorithm. So I'm going to change colors here, blue. So we need to construct the heap, this small one, right? And this small one. And this is small one. And this is small one, right? How many of those I have in this case? How many subtrees, small subtrees? Tell me, how many? for this case in particular?
4.
4, yeah. So I have 1, 2, 3, 4, right? 4 blue ones, small. What is the height of those trees? And the question is, what is the cost for constructing this heap, the small heap? One comparison here and one comparison there. And the height is, what is the height of that tree? What is the height of the blue tree?
1.
1, yes. So I have 4 subtrees of height 1, and the cost in the worst case is comparing this one and this one, right? And I have the arrangement of the trees, right? So I take 2 comparisons, right, to do this, right? 2 comparisons to do this, and 2 comparisons to do this, 2 comparisons to do this, right? And 1 is the height of that tree. So is that clear? No, but we just constructed the smallest tree. So we need to go up to construct, the whole heap sort. Now I'm going to change the color. I'm going to say green, right? The green is to construct this subtree. How many subtrees do I have?
2.
2. 1 here and 2 here. What is the height of those trees?
2.
2.
2. Right, I have 2 subtrees. And what is the cost in the worst case to arrange these subtrees?
For each one?
For each one, yes.
6 comparisons?
Aquí is here 1 and 2.
Okay.
And then it's going, this one, in the worst case, is going to be in one of the leaves, right? So it's going to take 2 comparisons per level, right? In order to leave this tree in correct order, right? Now I have less number of trees, but they are with a larger depth, right? So those are the greens. I have 2 height and 2 comparisons per level, right? Per level, because the element here is going to go to one of the leaves, but to one of the sides, depending on the comparison there, right? And the other is, we put another color here, which is this one. Okay, so now I have to construct the whole tree, right? The whole heap, I would say. How many trees do I have of this size?
1.
1, right? And what is the height of this purple tree?
3.
It's going to be 3, right? So I have 1 tree, this is 3. And what is the cost, to constructing the heap? This
2.
element is going to go all the way down. So it's going to be 2, 2, 2. So the number of comparisons is going to be 2 times 3, right? So is that understood? Understood the way you construct the heap? does this guarantee that you at the end have a heap of this size? Right? So on one side, again, I have one node, and for each node, I'm going to use two comparisons, right? Let me see if I have it here. Better written. Construction. Okay, let me just see the expression there. So let me see if I have the beginning. I have 4. Let me just erase this. I want to count the complete number of comparisons, right? For this, I have 4 nodes, right? And for each one, I use 2 comparisons, right? To construct the blue ones. And I have 4 of those, right? And then the green ones, I have 2, right? But the height is what? 2 times 1 is 2 trees and 2 comparisons per level. And how many levels do I have? 2, right? And for the purple, I have 1, right? 2 comparisons per level, and I have 3 levels. You see? And I need to sum up this plus this, and this is going to give me the whole number of comparisons for this phase, for the construction phase, right? So let me just return to color. 4 trees times 2 per level, just 1 level. Next, 2 trees, 2 per level, but 2 levels, right? 1 tree plus 2 comparisons per level, 3 levels. Total is the number of comparisons, right, for constructing the heap. So, do you understand this behavior? So we're counting the blue ones, the green ones, and the purple one, right? But I have number of trees on one side and height of each of the trees, and the number of comparisons at each level, right? And I have a total here. What do you think is going to be the complexity of this phase, constructing the heap? So the next slide is the answer, right? Let D equals log of n. Why is log of n? What is log of n?
The depth.
The depth of the tree width and nodes, right? Which is the number of nodes that I have in the array. The number of comparisons to create the heap in the worst case is twice the depth of the subtree root, right? And then the number of comparisons done by the heap construction is at most this, from 0 to d minus 1 times 2, d minus L, which is the height, right? And the number of multiplied by the number of nodes at level L, right? So the reason of this and this is that, you know, you have more trees, but you have less height. You have less trees, but the height is higher. So that's the reason this is changing. So you have this expression here, right? You reduce the height, but you increase the number of nodes or trees, also trees. So this is the expression, the general expression. This expression that I just put here is this expression here, right? Number of nodes are increasing in powers of 2, right? While the height is decreasing, right? And you go from 0 to d minus 1, right? And 2 is because you do two multiplications, two comparisons, sorry, to arrange the elements. Now, if we solve this equation here, is something like this. Well, if you solve it, this. So you're going to have the summation of d 2 to the L with this just giving a constant, and then the other is L 2 to the L. So if you solve it, you're going to have 2 to the d plus 2, and then minus 2d minus 4. And this is the largest term, which is 2 to the d is log of n, right? So this is more or less n multiplied by 4, which is a constant. So the complexity is going to be linear. The heap construction is in linear time, so it's not too costly. Does that make sense? That the construction heap is linear. So what do you expect here? This part is linear. And we need to count the comparisons in this one. What do you expect to be the complexity of the cycles here? What do you think is going to be the complexity of the cycle? Because I have two phases, this one separate from this one. So what is the complexity in order to say the overall complexity of the heap sort? What should I put here? That's the complexity of the cycle. What do you think it is? Any ideas? Any ideas? Or no idea at all?
No idea.
No idea at all? Why? This is a sorting algorithm, right? So the least number of comparisons
And
that
log
the
n?
algorithm is going to be n log n, right? So what do you expect to have in the cycle?
And log n?
N log n, right? Because this is just linear. So the segment that is going to give you the whole complexity of the algorithm is something here, right? Because I cannot do less than this, right? So I expect that this part in the cycle is going to be n log n. So can we show that? Let's do that. So, sorry, do you understand what I'm saying or not? Because I have two phases in the algorithm, right? And then with the complexity of the two phases, I'm going to get the complexity of the whole algorithm. If this is n, this should be n log n, right? In order to say that this algorithm is going to be n log n. Can we show that?
But sorry, doctor,
Yes.
that's only if the algorithm is optimal, right?
To be optimal has to be n log n.
Yeah, okay. But
Right?
it could be something else, right? Like
Could
higher.
be something else. Yeah, you are right. Yes. But at least all the the least number of comparisons in this part should be this, right? Can
Yes.
be more than that, but yes, we would expect that it is this in order to be optimal. But let's try, right? This part, okay? So I have, this is for the construction, right? So it's linear. And this is the heap fix, what is called heap fix, right? I take the largest element, I put it in the root, I put it in the last position of the array, and then I rearrange, right, the heap, right? The number of comparisons to fix a heap with k node is at most 2, right, per level, and this is the number of levels, right, of the heap. But the k is going to be decreasing every time, right? So it's going to start in n minus 1, you see here, and until 1, right? N minus 1, the height, and log k. So the number of operation, right, is going to be this expression. Now, tell me if you understand this expression. What is it? What is it? You know, what is the number 2 there? Someone.
Maybe it's
tell
for
me.
the split. Maybe it means for the split of into two parts.
Now, remember, I need to, the cycle is going to, you know, take this element and put it in the right position, the last position. But this element that I'm swapping, I'm going to put it at the last level because it's a worst case, right? It's the worst case. So I need to compare with this and with this, right? And then I go on one side and I say, I compare with these two and with the element that I have. So the 2 is the comparisons that I do at each level. Is that clear?
Yes.
And log of k is what?
The depth.
The
depth.
height of the tree with k elements, but k is decreasing every time from n minus 1, n minus 2, n minus 3 to 1, right? That's the reason I need to sum up, you know, the cost of, you know, fixing the heap for all the cases. So do you understand this equation here? The
Yes,
2
just
is the number of comparisons for each level, and log of k is the number of levels, right? Or a tree with k elements. But k is, in fact, is decreasing, but you can say it's increasing from 1 to n minus 1, the same, right? So if I solve this equation, I'm going to get the complexity of the heap fix phase, right? D is what? The
the
depth, right? Of heap with n element. So the sum, I do the same, more or less, what is the sum of log of k? K is equal to 1 to n minus 1. Have you seen this expression before? What is it? What is that expression? Log of 1 plus log of 2 plus log of 3 plus log of 4 plus log of n minus 1. What is that expression? We saw this expression in the last session. What is that expression?
That's when we use the integral to approximate the sum.
To approximate the sum of the log of n factorial, remember. What is log of n factorial? Log of n plus log of n minus 1 plus log of n minus 2, etc., right? So what do you expect with this expression here? Are you following me or not? Remember the log of n factorial? Yes or not?
Yes, I don't know it by heart. I'm looking.
Yeah, just, the lower bound of, what is log of n factorial? Log of n times n minus 1 times n minus 2, etc. So this is log of n plus log of n minus 1 plus log of n minus 2, etc. Does this look like this or not?
Yeah.
It is, right? That's the reason this expression is going to get you n log n, right? Which is the complexity of the heap fix, and which is the complexity that we expected to have, right, for this algorithm. Is it true or not? Am I making sense or not?
Yes.
Yes.
So you have this expression. If you solve it, you're going to get all this, but at the end, you're going to have this complexity, right? So I have two things, right? Here. Constructing the heap, what is the cost? Linear. Rearranging the heap, or which is the fixed heap, and log n, right? Total complexity, the largest of these two, which is
N log n.
n log n. Is this algorithm optimal?
Yes.
Yes, it is. It is. Okay, so that's the analysis for this algorithm, right? And this is a binary tree. So I'll give you an exercise in the homework in which the heap is not binary. The heap is ternary. So you have 3 zones for each node. And you check if the analysis changes for that. But you understand the construction, you understand the rearrangement, and you understand the total complexity that you get. So take a look at this, the construction, and take a look at this, the heap fix. But this expression, right, is similar to log of n factorial. And easily, when you see log of n factorial, okay, I know that that is n log n, right? Clear enough? Questions? Do you understand the heap sort? How it works? More or less? Good?
Yes, good.
Okay. This is what I want to hear. If not, tell me, please. Right? If not, just tell me. But I have 2 phases here, the construction, from bottom to top, going from smaller subtrees up to the one up, the large heap. And it makes sense because the construction complexity, because you have more smaller subtrees with a small height, and as long as you increase the size, you have less number of trees. So while one thing is going to increase, the other is decreasing. So that's the reason it's like compensates, right? And then you get the complexity the linear complexity for that phase. In this case, you get this expression, and this expression is similar to log of n factorial, and you know that log of n factorial is going to behave like n log n. So that's the part of the heap, right? So this is the second topic today. What do you think? It's a different algorithm, works different way, right? And for the average case, analysis for the heap sort is very complex. I don't know, it's somewhere, I think in the notes, book, but it's, very complex because you don't know exactly the probabilities of putting the element somewhere, right? Of the inputs, for the heap, because there's a relationship between the numbers, right, and the way they are going to be in the heap. So it's not too easy, right? So that's the reason we check only a worst case here in this module. Okay. So questions so far. So we checked the merge sort based on the merge structure, and we checked the heap sort based on the heap structure, right? So those are different algorithms from the previous algorithms we checked in the last session, right? Last week. So are we doing okay? Let's go to the last topic. I know you may be tired, but be patient a little bit. So I'm going to try to show you the lower bound of sorting in the average case, right? And let me just give you the basis for this. When we did the lower bound of the sorting problem in the worst case, remember, we had a comparison tree. And at the end, in the leaves, we have the sortings, all the possible sorting or permutations, right? And we looked for the branch that took me to the largest path, right? To one of the permutation, which was the worst case. And that was given by log of n factorial, right? That was the worst case. Now, with the average case, what we are going to do is just to say, what if I consider all the possible sortings, right? And then I say, there's a cost for getting here. There's a cost for getting here. There's a cost for, number of comparisons for each of the cases, for all the cases. And then I sum up this, plus this, plus this, plus this, right? And I put it here, the summation, and I divide by the number of leaves or number of permutations that I have. For the general case, it's going to be n factorial, right? And this is going to give you n log n for the average case. So what I'm stating here is clear that I need to sum up all the paths to all the permutations in the leaves, sum them up, and divide by the number of leaves, right? Which is the number of all permutations that I have, which is n factorial, and then I have n log n. So is that clear what I want to do? Hmm? Yes or not? Well, okay, let's try. The external path length of a tree is the sum of the lengths of all paths from the root to a leaf. And this is going to be denoted by EPL. So it's like the EPL of a tree is from this, from this, from this, from this, from this, you know, the sum of lengths of all paths from the root to the leaf, right? So it's like I'm trying to find this summation. A binary tree in which every node has degree 0 or 2 is called 2, 3. Means that the nodes have 0 offspring or 2 offsprings, right? That is a called 2, 2, 3, 2, 3, right? So let me just put you an example. So what is the EPL for this tree? To this node is 1, 2, 3. To this node, 1, 2, 3. To this node is 3, right? To this node is 2, and to this node is 2, right? So the EPL for that tree is 13, right? The sum of all paths from the root to the leaves, basically, right? And then the 2 trees is, you know, the ones, well, this actually is not a 2, 3, it should be like here, because the 2, 3, 0 offsprings or 2 offsprings. And there's a reason for that. So there's 3 plus 3 here, which is 16, right? So that's the EPL. Between 2 trees with L leaves, here I have a leaves, in this case 6, the EPL is minimized only if the leaves are up to 2 adjacent levels. So if I have the leaves at 2 levels, the EPL is minimized. And I want to consider this because I want to minimize, you know, the sum up here against the number of leaves here, right? So, and there, this is a lemma, that is true. And there's a demonstration there, right? And the explanation in here, I don't want you to go to all the details, but the demonstration here, right, meets this lemma in particular. So I want to have, you know, the leaves at most 2 levels, right? At most 2 levels. So the EPL is going to be this value, and this here is a demonstration for which this case is true, right? So it's like if we put the leaves at 2 levels, the EPL is going to be minimized. So just review this a little bit, right? And it's also in the book, right? Now, the minimum EPL for 2 trees with L leaves is Logobel. Let me see. I'm going to give you an example again. So I have how many leaves here? 1, 2, 3, 4, 5, 6. What is log of L? Floor. Log of 6, floor. is what? What is log of 6? Floor. Tell me, please. Log of 6 floor. Log
Two?
of 6 is 2, right? Okay, so 6 times 2. So I'm just using this expression here, right? And I'm trying to get the EPL. And then 2. So for the 6 leaves, I'm counting the EPL 1, 2, up to here, up to this level, right? This is L log of L floor, right? And I need to count all these parts. So what is L minus 2 to the log of L? 6 minus 2 to the 2. What is that? What
2.
is this value? 2. And what is the meaning of these 2? Is the nodes that have children or offspring, right? This is the L minus 2 to the log of L times 2. Times 2. And what is the 2 here? That each one is going to have 2 children, right? So I need to count them. So I have here 2 times 2. So this is the EPL. 6 times 2 and 2 times 2, which is 416, right? That is the EPL of this tree in particular, right? And you see, this is 1, 2, 3, 6, 9, 12, and this is that true? Okay. 3, 3, 3, 3, 2, and 2. Okay, that is 16. Yeah. Okay. So this is the minimum EPL is given by this. What if the tree is complete? What if the tree is complete? For example, 1, 2, 3, 7, 8. What is the number of leaves here? The number of leaves is what? 1, 2, 3, 4, 5, 8. Right? Log of 8 is 3, right? Plus, what is this? 2 L, which is 8, minus 2 to the 3. This is what? This is 0, right? So when I have a complete tree, this is the expression that is going to count because I don't have elements, right, at a different level. So so this is just for counting the EPL, right? So what I did is, this explanation here, Now, the average EPL in a 2-tree with L leaves is at least log of L. Okay, how do I demonstrate that? Is that I have the expression here. You see this expression, L log L plus 2 L minus 2 to the log of L is this expression, right? Divided by L, because I want to get the average EPL. And what is that value? L log L over L is what? Log of L, right? And this over L is going to be a constant, a value that is between 0 and 1, right? And then this is a constant, right? So the average EPL is going to be log of L. And what is log of L? What is log of L? What is the number of leaves that I have in a tree, in a sorting problem? What is L? What is the number of leaves that I have? All the possible permutations, right? In an array, how many? How many? How many permutations in an array of in elements? How many? Remember? How many different orderings in the leaves of an array? How many? In factorial, right? So this expression is log of n factorial, and this expression is log n. So that's the reason, right? The complexity is n log n for the average case of the sorting problem. Does that make sense? So what do you have to learn out of this? That the lower bound of the sorting problem in the average case is also n log n. So why is this important? Because you have an algorithm. You say, okay, I need to check if this algorithm is optimal, and then you have two cases, right? I analyze it in the worst case, and then I have to compare it against n log n, right? And you say, well, I have the algorithm, I do the analysis in the average case, and in order to know if the algorithm is optimal, I'm going to compare it against what? N log n, too, right? Because it's the lower bound in the average case. Okay, so tell me if there's any questions related to this. This is the third topic today. What do you think? Merge, sort, keep sort, and the lower bound of the sorting problem in the average case. Is that okay? What do you think? Brenda, Alejandro, Cesar, Raquel, Miguel,
I
Daniel.
understood some things I need to review.
Yes, you need to check it out again, I think. Right. But most important thing is, the way the algorithm work, and also the way we compute the complexity, right? Because it's different for each algorithm. It is important to know, the process for each algorithm and see what the algorithm is doing on one side, and, checking the number of comparisons that the algorithm is going to provide. Okay? So, are we ready to check the homework? By the way, I just changed the due date for the first for homeworks, and so the deadline is going to be on Sunday at midnight. Okay, so it's already in Canvas. Let me see. I have the homework number 5, and this homework is going to be due on April, after Easter week. Right, Easter week I think is from the 13th to 20th of April. So the homework should be submitted on the 22nd, because the exam is going to be on the 28th of April, So we need to, you need to submit all the 7 homeworks and then give you some, at least, the feedback of the first 4 homeworks and also solutions for all the homeworks, right? So you can study that week, right, before the midterm exam, which is on the 28th, more or less. But we review the dates later, right? So let me just share the homework number 5. So can you see my screen there?
Yes.
Okay, so this is today, and well, I still state that the homework should be submitted in a week, right? That is not the case. Like, you know how this works. Okay, so the first exercise is to implement the algorithms quick sort, merge sort, and heap sort in any programming language of your convenience and investigate their performance in arrays of 100, 1,000, 10,000, 100,000, and 1,000,000. For each of those sizes, consider the files randomly generated integers, files with integers already sorted in ascending order, and files with integers already sorting in descending order, right? But those are not the cases, of course. Some try some unsorted array, right? Hand in and report with your investigation containing the analysis, discussion of results, and the conclusion. So that is a small implementation work, and then the report. And the idea is, to see how they work, the different algorithms and how they behave for different cases, right? Is that okay? Do you understand the first exercise? Yes or no? Yes.
Yes.
Okay. And then the second is consider a theory heap. Instead of binary, it's going to be, ternary, I would say, right? Similar to the binary tree, except that the no-leaf node has 3 siblings, right? 3 offsprings instead of 2. How would you represent the theory heap in an array? What is the length of the 3D heap with an element in terms of D equal to 3 and N, right? For an element in position I in the heap, determine the position of the parent and sibling. In general terms, determine the complexity of the heap sort algorithm with these features. So it changes a little bit, but you tell me what you find, right? Suppose this is number 2, right? Number 3, suppose you're given a set of K of lists equal size, totaling n elements. The items in each list are already sorted. Provide an algorithm and its complexity to merge the sublists into one sorted list of n elements. All right? So you have sublists, small sublists, similar size. You have K sublists, and you have to merge them in order to generate the sorted array. So provide the algorithm and the complexity to do that, right? And now you're going to describe an algorithm that makes 38 comparisons for sorting 14 elements in the worst case. So you have to go to this document included in the Nuth book, volume 3. And what you have to do is, to go through the go through the algorithm and try to work it out with 14 elements that you generate the elements there, and then you see step by step how the algorithm works. So so I'm including in the homework this document, right? So for example, here, what you have to do is follow, the steps in the algorithm. And at the end, there's a table here for which you have the number of elements here, 14, for example, and then you say for 14 elements, the number of comparisons that the algorithm does is 38, you see, right here. And then you have to understand what the algorithm does, basically, and explain it in the homework. Okay, so that is homework number 5. So just upload it to Canvas, right, with your information there, and it's also by couples. Okay, so questions so far? Are we doing okay? So this is the fifth session of the semester. We still have to do 2 more before the midterm exam, which is one of them, the 6th session is about selection problems. So you have a set of elements and you want to select a particular one. So this node algorithm, we're going to use it, right, in the analysis of the complexity of the one general algorithm that we are going to explain in detail. Right, so that is session number 6, and session number 7 is about a matrix multiplication and polynomial evaluation. Also some algorithms there. So those are the 7 sessions that will be included in the midterm exam. Right. So any questions about all this? Everything is okay?
Yes.
There's so many, well, the material has been, piled up throughout the week. So you have a lot of work to do and also a lot of things to study, etc., etc. But I hope it's worth at the end, right? That's my purpose, and I expect that we fulfill that, right? So questions before we go. So I will upload the homework just in a little bit, and also the recording. Good? Well,
Yes.
okay. Thank you very much.